Hello all. Now we are going to discuss about the concept of pumping lemma for context-free languages. So in formal language of theory, the pumping lemma for context-free language is also known as the Bar-Heil lemma. This lemma gives a property shared by CFLs. Pumping lemma for CFL describes a property that all the CFL are guaranteed to have. All the strings in the language must have a length of at least p, where this p is called the pumping length and it is a constant value. Informally, it says that all long words in CFL can be pumped. That is, the middle section of the word is repeated n number of times to produce a new word, which also lies within the same language. So the process of pumping up additional copies of string gives the name pumping lemma. It was first proved by Dana Scott and Michael Rabin in 1959 and was rediscovered shortly by Ellie Shammer and Micah Pearls in 1961 as a simplification pumping lemma for CFL. So now comes the definition of pumping lemma. Let L be a context-free language. Then there is a constant n, which depends only on language L such that there exists a string z. It belongs to this language and modulus of z should be always greater than the value of n, where this n is the length of the string. And z, we are going to define z as u, v, w, x and y. These are all the substrings. So the conditions are, there are three conditions not to prove the pumping lemma. First one is modulus of v, w, x must be less than n. And then the modulus of vx should be greater than 1. And then for all u, v power I, w, x power I and y, it must belong to this language L, where I should always be greater than or equal to 0. So now let us see an example so that the concept of pumping lemma will be clearly understood. And using the pumping lemma, we are going to prove the following language is not CFL. 0 power n, 1 power n, 2 power n. And this n value should always be greater than or equal to 1. And this language consists of strings like 0, 1, 2, and the condition for writing this language is 0 should be followed by 1 and should be followed by 2, and there must be equal number of 0s, 1s and 2s. So from this language I am going to take a string 0, 1, 1, 2, 2. So 0 is taken as u value, 0, 1 is taken as a value of v, and 1 is taken as a value of w, and these two I am going to take as a value of x and y. So first is case 1. I am going to prove that the modulus of v, w, x should be less than or equal to n. So modulus of v, w, x is 2 plus 1 plus 1, that is the value of v is 2 and the value of w is 1 and value of x is 1. So obviously 4 will be less than 6, and this 6 is the length of a string. The string which I have chosen is this, and the length of this string is 6. So it is obviously less than the 6, and this condition is satisfied. And next comes this case 2. The modulus of vx should be greater than 1, and the v value is 2 and x value is 1. So, therefore the 3 is greater than 1, and this condition is also satisfied. Next comes the third condition, u, v power I, w, x power y should belong to this language, and this I value can be any value, and as per the definition it must be greater than 0, and I am going to take this I value as 2. So 0 is my u value and v power I. So I am going to repeat the strings for 2 times since I value is 2. So this is v, and this becomes w's value, and x power I. X value is 2, since x power I am going to write that 2 for 2 times, and this value is y. So this language does not belong to our language 0 power n, 1 power n and 2 power n, since 0 is not followed by 1 and not followed by 2. So by the pumping lemma we have proved that the language is not a context-free language. Thank you all. Hope this video will be useful for you.